Hello and welcome to Mr. Linford's Math 097 course. This is a presentation on section 3.1 of the text. In today's discussion, we're going to be exploring what a function is. In particular, we're going to be looking at the definition for a function. We're also going to be looking at different graphs, seeing if we can determine from a specific graph whether or not we have a function. We're going to look at the vertical line test in particular for that, and as well we're going to be working with how to evaluate functions. To start things off, we're talking about functions. We have to actually define what it is. A lot of times in previous math classes, teachers just say a function is, it's just an equation, or it's an input-output. Well, sometimes functions can be thought of as behaving that way, but there's a much more deeper and richer definition to this. So I'm going to write down the definition for a function. This actually comes from our textbook, and what we're going to do is we're going to kind of pick it apart. Now this is a bit of a lengthy definition, so I'm going to start writing up here. For a function, given a relation in x and y. Y is a function of x if for each element x in the domain, there is exactly one value of y in the range. Okay. Let's try to pick apart this definition. It's very lengthy, it's very specific in how it's worded. To have a function, you must first have a relation. You must have a relation in x and y. Remember, a relation is a set of ordered pairs. That looks terrible. Ordered pairs. That's what a relation is. So we have a set of ordered pairs here. We have a relation. But we are picking those ordered pairs very specifically. They must meet two conditions. One of the conditions we call is domain complete. Domain complete means that everything in the domain is mapped over to something in the range. I'm not leaving random domain values without being paired up to a range value. The second component is what we call function-like. Now, function-like means that for every domain value, there is a range value. But more specifically, for a given domain value, there is only one range value. Okay? A domain value is paired up with only one range value. Only one range value for a domain value. That's an important idea, and we're going to use this idea of function-like to really help us determine whether or not something is in fact a function. So we have an example right here of 1, 4, 2, 5, and 3, 6. Here are three ordered pairs. This is a relation because a relation is just a set of ordered pairs. Well, I want to determine, is this relation a function? To do this, I'm actually going to draw a little correspondence diagram. That's where we have the two ovals, and I'm going to put the domain in one and the range in the other. Here's the domain, here's the range. And let's show how the domain and range are related. Because of the ordered pairs, we're saying 1 is mapped to 4, 2 is mapped to 5, and 3 is mapped to 6. I'm using the word mapped. You can say paired up with or linked up with. 1 is paired up with 4, 2 is paired up with 5, 3 is paired up with 6. Somehow you took the domain value of 1, you did something to it, and you turned it into 4. Same thing with taking the domain value of 2, doing something to it, and turning it into 5, and 3 turning into 6. So here's our relation. I want us to determine, is this in fact a function? Well, there are two things to check off. Is this function domain complete? That's the first part. Well, take a look at your domain. Everything in this domain is paired up with something in the range. So, in fact, we actually are domain complete. So there we go. The first part of the definition is met. The second part is the one where it gets kind of tricky. Is this function-like? Remember, function-like means that every domain value is paired up with only one range value. Let's see here. Let's go through the domain, and let's see if each domain value is paired up with only one range value. 1, well, that only goes to 4. 2, well, that only goes to 5, and 3 only goes to 6. So it looks like every domain value has only one range value. So this is function-like. So since it's domain complete and function-like, we are going to say that this right here is a function. It is a function. It satisfies our definition. Now, let's use this idea to kind of practice a couple different examples. Let's say I had these correspondence diagrams drawn, and I want to know which of these are functions. Well, just ask yourself the two parts of the definition. Is it domain complete, and is it function-like? So first up, for number 1 here, is this domain complete? Well, hopefully you're saying very quickly, no, it's not. Because look at that 3, it's by itself. It is not paired up with anything in the range. So this is not domain complete. I'll abbreviate it DC. So this is not a function. Let's take a look at the next one. 1 is paired up with 4, 2 is paired up with 5, and we have this 6 all by itself. So let's ask ourselves, is this domain complete? Pause the video, take a second to think about it, and return with whether or not this particular relation right here is domain complete. All right, well, hopefully you had a chance to pause the video and think about this. Is this relation, this number 2 relation here, is it domain complete? The answer is yes, it actually is. A lot of people get tripped up because they see this 6 all by itself right here. This is kind of a trick. Remember, the definition says that we want the domain to be complete. It does not say anything about the range. So I kind of don't care that this 6 is all by itself here. I really don't care about that. All I want to do is make sure that the domain values are in fact paired up with stuff in the range, and they are. Now, since it's domain complete, let's check to see if it's function-like. Do all of the domain values go to only one range value? Well, this one does, and this one does. So it looks like we're good. This is, in fact, domain complete and function-like. So this is a function. There we go. So we notice that really we have to be careful with how we interpret the definition by knowing that domain complete doesn't tell us anything about the range. All right, let's take a look at the next one. In this problem, we are mapping 1 to 4, 2 to 5, and 3 to 5. All right. Is it domain complete? Well, yeah, just look at the correspondence diagram. Every domain value is paired up with something in the range. So this is domain complete. Now the trouble is it function-like? Pause the video, take a minute to think about it to yourself, and come back whether or not this satisfies the definition of what it means to be function-like. All right, well, hopefully you had some time to think about it. A big area that people struggle with when they think about whether or not it's function-like is this issue right here. How 2 and 3 are both mapped to 5. The 2 domain values are going to a single range value. And that's the question, is that allowed? Is that possible? Can we have this? Does it satisfy our definition? Well, remember what it says to be function-like. Function-like says only one range value for a domain value. Only one range value for a domain value. Ask yourself, does 2 have only one range value? Well, yes, it does. There's only one branch coming off of 2. Does 3 have only one range value? Well, 3 gives you 5. So yeah, each of those have only one range value. So this example right here is function-like. This is a function. Because the definition says the domain value must have only one range value. It never said that they can't have the same range value. It just said, I want each domain to only be linked up with one range. Never specified that it didn't have to be the same range value. So you can see why we're being very careful and kind of tricky with our definitions. Now the next example. Let's take a look and see, is this domain complete? Well, yeah, it's pretty obvious. Number 4 here, yeah, domain complete, because everything in the domain is paired up with something in the range. Now, is this function-like? Is the domain values only going to one range value? In here, 1 is going to 4, 3 is going to 6, and 2 is going to 5, and it's going to 4. Pause the video, take a minute, and think. Is this function-like? Are the domain values, is each domain value going to one specific range value? All right, well, hopefully you had some time to think about this. But let's think, is this function-like? Does each thing in the domain go to one thing in the range? Well, 1 only goes to 4, so that's good. 3 only goes to 6, so that's good. Here is the problem, 2. 2, if you plug 2 in, you're going to get 4 or 5. 2 gets mapped to 4 and it gets mapped to 5. That's our problem here. This is the issue. This is not function-like. I'll abbreviate that, FL. This is not function-like, so this is not a function. All because the domain value went to multiple range values. We were allowed to have a single range value for multiple domains. That's not what function-like said, so that's why we were allowed to have this. This is what we couldn't have, where a single domain gives you 2 range values. Hopefully now you're seeing kind of how this definition is playing out and how we have to be very careful with some of it. But remember, relations aren't really always just these simple couple finite collection of points. Oftentimes they're infinite. They have infinitely many points. So when we have infinitely many points, I often think of, well, a graph. So when we look at this graph, or these graphs I should say, we want to determine, are these graphs functions? Do they satisfy the definition? Now, I will give you a little heads up. All of these graphs are domain complete. It'd be very difficult for me to draw something not domain complete. Sometimes people say, just put a hole in the graph. Well, if there's a hole in the graph, then really that point isn't even in the domain, so the graph is still technically domain complete. Either way, that's getting way too technical with some of this stuff. What I want us to really look at here is determine, are these graphs function-like? Do these graphs satisfy that for a single domain, you get one range value? Well, if we think about that, are these function-like? That's what we're testing here. One domain gets one range. And maybe I shouldn't say one domain. Let's just say each thing in the domain gets one thing in the range. So what would that mean as far as, like, let's say a graph here? Remember, the domain is x, and each x has a single y value. So if we were to have some x value, like let's say this example right here, this x, would it give us a single y value? Well, yeah, this x gives us this y value, this coordinate point. Okay, so I'm going to say that this is probably a function. This linear line right here, I'm going to say it's probably a function. Then let's take a look at this middle one right here, number 6. This is an ellipse. So let me pick this x value. Notice how, oh, there's a y value right there, and there's a y value right there. There's 2 coordinate points for this x value. This x value has a y value up here and a y value down here. This single x is giving us multiple y values. I'm going to bet and say that this is not a function, just because that single x value gave us 2 y values. Well, let's take a look at this parabola here. Let's take, I don't know, this x value. And, it has 1 y value. Let me think, is there any point on the graph where I have some x value giving me multiple y values? Well, it doesn't really look like that. Each x seems to only give me one coordinate point. So I'm actually going to say this is probably going to be a function. And then the last one, this is actually what's called a cardioid. And I'm going to pick an x value, I don't know, like let's say this one. This x value, it's close to -4. I'm seeing 2 y values, 2 coordinate points it produces. So for the single x value, I get 2 y values. This should not be a function. So we're kind of seeing a little pattern here. We're seeing for a single x, look if there are 2 y values. And I'm not just checking one point here. We got to be checking all of these points and see, are there multiple y values? But I can kind of do that a little visually. And in fact, there's a technique for doing this, and it's called the vertical line test. The vertical line test says, I'll say step 1, make a vertical, I'll abbreviate it vert, a vertical line on the graph. And when I say make a vertical line, imagine in your head that you have some vertical line, or use your pen or pencil or something. Oh, that was a terrible 2. Step 2, we are going to slide the vertical line oh my gosh, my handwriting is terrible today. You know, I'm practicing as much as I can on the stylus, but it doesn't seem to do any better. Maybe just because I have bad handwriting to begin with. But once we have this vertical line on the graph, we want to move it around. Slide the vertical line across the graph. Across the graph. And what we're doing is, step 3, we are checking to see if it crosses more than once. Okay, you get the idea. The idea with that vertical line is we're going to make a vertical line. Here, I'll make it in blue. And we're going to kind of move this vertical line along the graph. And what we want to do is we want to check to see, does it ever intersect the graph more than once? Well, in all of these examples, I'm seeing the the vertical line not intersect the graph more than one time. It only happens one time. So as we previously saw, this seems to mean that the graph is going to be function-like. So I'm going to say that this first graph is a function, because the lines only intersected at one time. Now, for number 2, this is a sideways parabola. This is actually y squared equals x. I just drew one vertical line, and look, it crosses at 2 points. That's an issue. Right away, I know that this is not a function. Let's keep practicing this. I have this horizontal line here. I can make a bunch of vertical lines. I can kind of, in my head, visualize as they move along the graph. They're only intersecting one time each time. Each of these vertical lines only intersects once. This is going to be a function. Now, we have this very sad-looking circle. Go ahead and draw one line. You can see right away it intersects more than one time. This is not a function. And for the last one, you know, I'm going to draw this line right here. And what do you know? I crossed the graph actually 3 times. So again, not a function. The big idea here with the vertical line test is that the vertical line test is going to basically check if the relation is function-like. That's what it checks. It checks if it's function-like. And if it is function-like, then we know we have a function to it. Again, the domain complete, you can kind of just assume for everything we do in class, all these graphs are going to be domain complete. Now that we have an understanding of what's a function, what's its definition, and how to really quickly determine whether or not a given relation or even a given graph is a function, let's actually go ahead and start evaluating them. Let's start figuring out different points for a function. Before we begin, there's some notation you need to know. A function has a name. We're going to be working with multiple functions at a time. We have to distinguish one function from the other. So we're going to name the function. We're going to have a letter that designates this is function f, this is function g, this is function h. Don't be that person that if you had some graph and you had a bunch of functions on it, all these various functions doing all this different stuff, and you named all of them f. This is something I've actually seen before. And you try to specify which function is which because they all have the same name. That's going to be a bit of an issue. So we are going to actually name our functions. Additionally, we're going to distinguish what the variable is. When we write a function, we are going to want to actually say what the variable for this particular function is going to be. Now, when we piece the name and the variable together, we get something like this. It might be a little hard to see, but it is f and x in parentheses. We write this, we call this f of x. This is the output, kind of like y was in an equation. This is the output. So if you see this function, we have f of x equals 2x plus 1. The name of the function is f. So if we're talking about a function, right now we'd say, oh, function f, and we know which specific one we're talking about. And the actual function itself is 2x plus 1. And you know what? Just in case you're wondering, the variable, it's going to be x. That's the thing that's going to be the variable for us. This is helpful when we have multivariables or when I start bringing in different symbols for different constants and we have something like a literal equation. It's helpful to know what's the function. But here's our example. Here's the function f of x equals 2x plus 1. This is very much like the equation y equals 2x plus 1. All I'm saying is it just satisfies a little bit extra of a definition. What we want to do with this function, we want to determine what a point is on the function. What would happen with f of 2? If you see f of 2, what they're saying is take the function f and plug 2 in for x. I'm actually going to plug in 2 for the x value. The x here, this variable, is your input. This is where you are plugging things in. This is saying, this notation right here says, plug 2 in for x. We want to figure out what is the function equal when x is equal to 2. So we plug that right in. And we get, let's see, 2 times 2 is 4. 4 plus 1 is 5. We get 5. So we get the coordinate point 2, 5. When x is 2, f of x, or we'll say y, is 5. This tells us a coordinate point. We can make a graph from this. Functions, they behave very similar to equations. When your teacher said in the past, functions, think of them as equations, they were partially right. Because functions, they look like equations, they behave like equations, they graph like equations. In this example, we have a slope, we have a y-intercept. Everything behaves just like normal. The only difference is, instead of having a y, I have this f of x symbol. And this is telling me that I have a function here. I have something that's not just a simple equation, but it's a relation. It's a set of points that meets very specific definitions. Let's practice evaluating some of these functions. First up, we have f of -1. This says take the function f and plug -1 in for x. So I take -1, I square it, and I subtract 2. -1 squared is 1, minus 2 is -1. So that should be my answer, -1. Notice a couple things here. I am making sure to write -1 in parentheses. Anytime you sub in for x, always write in parentheses, because there's a difference between -1 in parentheses squared and -1 not in parentheses squared. This is 1, this is -1. They are not the same thing. Okay, let's try another example, g of 0. This says take the function g and plug 0 in for it. So I take 4, I multiply, instead of by x, I plug 0 in, and I add 5. So that just becomes 0, so I end up with 5 as my answer. Seems okay so far? Let's try h of 3 now. Okay, this says take the function h and plug 3 into it. Okay, so here's my function h. I'm going to plug 3 in for x, and oh, wait a minute. This is an issue, isn't it? There's no x there. Well, what do I do? There's no x. Before we panic, think back to what would this be like as an equation? Y equals 1. We've seen this before. This was a constant equation. This was, if we plotted it on a graph, it would be a straight line at 1. It would be a straight horizontal line at y equals 1. We said that no matter what x is, because there's no place to plug in x here, our answer is always going to be 1. So since you can't really plug x in to the function h, because there is no x there, your answer is just going to be 1. Heck, you could take h of, let's take a million, h of a million. I guarantee you the answer is still going to be 1. It's the same thing every time. All right, now let's change things up a bit. Instead of working with plugging in numbers, let's try to plug in a variable. G of k. This says take your function g, so we got our function g, and we're going to plug k in for x. Well, let's do the exact same thing we did with the numbers. Before, when I had to plug 0 in, I just changed x to 0, but now I'm changing it to k. So that's my answer, 4k plus 5. All I did was I just plugged in a variable. That's actually allowed. It's totally acceptable to do. You can plug in a variable. And in fact, we're going to see in a couple sections what happens when we go and actually plug in full expressions in for the variable. That's the central idea to this section. We covered what is a function, what are the different components, being domain, complete, and function-like. We looked at how we can determine whether something is a function by looking at the graph and using the vertical line test. And then we also went about and actually trying to evaluate a couple functions for numbers and one for a variable. If you have any questions, comments, or would like to give me any feedback, feel free to email me at Linford, Linford, like the car company, at wccnet.edu. Until next time, take care, and I will see you again.